Today we're going to be taking a look at something called Pascal's triangle. And you may have heard of this before. It's got ridiculous number of different patterns in it that are of uses for different things. So you may have seen it for something other than what we're going to do with it today, or you may have seen it the same thing. I have no idea. But if this is the first time you're seeing it, it is actually a really, really, really cool pattern. So we're going to start off with just what Pascal's triangle is. And you'll notice for this purpose, I've drawn little hexagons in. They don't have to be inside hexagons. You can just write the numbers. So for instance, the part that's written there could just be written as 1, 1, 1, 1, 2, 1, and so on. However, I put the hexagons here to kind of really clarify where the numbers go. Basically, it's just every other row is offset from the row above it. So whenever we see a number, there's a number between any two numbers in the next row. The way that we get each of these numbers is actually pretty straightforward. So for instance, if I want to get this box here, I just add the two numbers that are diagonally above it and get a 4. Now, if I happen to be on the edge, I would add the 1 and nothing, so I get a 1. And because of that, all of our diagonals down the two sides are going to be nothing but 1s. So I'm just going to fill this in here. You can fill it in any way you'd like. You can pause and do it. You can jump forward after you've checked to make sure you've done it right, etc. In fact, I'm going to actually pause, fill it in, and then come back after we've done just a few more, just because it's time efficient to do it that way. So a few I'll fill in. 5 is 1 plus 4. 10 is 4 plus 6. 15 is 5 plus 10. 10 plus 10 is 20. 20 plus 15 is 35, and so on. So take a moment, fill that in. I'll do the same, and I'll meet you back here in about 2 seconds. And it looks a little bit something like that. Now this pattern can go on for as long as you want it to. We don't always need that much of it. Sometimes we need more of it. Sometimes we need part of it that is way too far down to bother drawing all of. And we'll get to how to draw that row without doing every other row before it in just a moment. Okay, so this doesn't look like it's highly related to what we're working on right now, which is combinations, but it turns out that despite the fact that this is not how it was just created by the pattern we said, where it was add the two numbers diagonally above. It turns out that this is actually ridiculously interesting when it comes to combinations. It turns out that every number in Pascal's triangle actually is a combination, and it follows this pattern. So I could replace all these numbers here. I'll try and do it just so I don't take up too much room. And I'm going to point out some of the properties that we already know about. For instance, anything choose 0 is just 1, because there's only one way to choose nothing, no matter how big a set you're choosing from. Anything choose itself is equal to 1, because if I have to choose everything, there's only one way that can happen. So these are all going to equal 1. Anything choose 1 is itself, because if I have 5 objects and I want to choose one of them, that can happen 5 ways and so on. So this row is just going to be 2, 3, 4, 5. Likewise, anything choose 1 is going to be equal to anything choose all but 1. So 3 choose 1 and 3 choose 2 are the same. 4 choose 1 and 4 choose 3 are the same. 5 choose 1, 5 choose 4 are the same. And now the rest of them, the pattern, of course, is exactly what we saw above, but it's not as obvious on how to explain it. 4 choose 2 does work out to be 6, which is the 3 plus the 3. 5 choose 2 works out to be 10, as does 5 choose 3, which again is the 4 plus the 6, or the 6 plus the 4. So every row in Pascal's triangle is just a whole lot of combinations. And what we can notice is that the top number tells us what row we're in from top to bottom. And we're going to start off with 0. So this is the n equals 0 row. The next one is the n equals 1 row, n equals 2 row, n equals 3 row, n equals 4, and n equals 5. Okay, so that's what determines the top number. And again, with Pascal's triangle, we start at zeros, not at ones, just because of the way it's designed. And then for our bottom number, I'm going to note that all of those are zeros in that diagonal all the way down. So that's r equals 0. This one here is r equals 1, r equals 2, r equals 3, 4, and 5. So the position in Pascal's triangle tells us what the combination is going to be. Starting from the top down, starting at 0, that gives us our top number for the combination. And going from left to right, or right to left to be honest, but for our purposes, left to right, starting at 0 will give us the R value, or the number that we're choosing. That's kind of interesting. There are a lot of properties here. A few of them I'm going to just kind of jump over quickly as interest's sake. They're not necessarily the ones we're going to use for problem solving. They're just kind of neat that they're there. The first one I'm going to look at is called the palindrome property, which is just a fancy way of saying that every row is the same whether you read it forwards or backwards. So just because I have it on the sheet, I'm going to look down there and say that that row is 1, 6, 15, 20, 15, 6, 1, which of course backwards is 1, 6, 15, 20, 15, 6, 1. And since we're on the topic of palindromes, I thought I'd share a couple of ones. Mom is a palindrome, M-O-M, spelled backwards is M-O-M. Dad, race car, spelled backwards is race car. And my favorite one, damn it, I'm mad, spelled backwards is damn it, I'm mad. Okay, that's palindromes. The Fibonacci sequence is another interesting pattern that shows up in Pascal's triangle. For those of you who aren't familiar with Fibonacci sequence, the idea is you start off with the pattern 1, 1, and then every number after that in the sequence is going to equal the sum of the two numbers before it. So the next number will be 1 plus 1 is 2. The one after that will be 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 13 plus 8 is 21, etc. Okay. Now to show that on the diagram itself there, I find this one personally a little bit hard to draw. I always draw it off and end up screwing it up. I will draw the next line in just to show you. And in order to do that, I'm going to have to put the 1 there so that we can see it clearly. But the next slant diagonal goes through these numbers. And that's going to be 1 plus 6 plus 10 plus 4 is 21. And sure enough, that is actually the next number in Fibonacci sequence. So it's interesting that this famous Fibonacci sequence actually is hidden within Pascal's triangle. This next one I find kind of interesting, but I think that's just because I'm Canadian, so I'm naturally, attracted to hockey. And that's called the hockey stick property. And the idea behind it is if you make a hockey stick like the ones in this picture, you'll notice that there's a hockey stick and then the hockey blade is kind of one extra piece at the end. So let me just try and highlight this as best I can. I'll use red to make it a little bit more obvious. So here, this hockey stick, and then there's the hockey blade at the end. And the neat thing is the blade, which in this case is 84, is equal to the sum of everything in the stick, the 56, 21, 6, and 1. And it will always work this way, as long as the hockey blade is just the one extra box, and the hockey stick goes from the diagonal above it all the way to the other end. Now, it's again not a coincidence why this works if we think about how we got these numbers in the first place. So let's take a look at that green hockey stick on the diagram, and I'll see if I can justify to you why it works. I'm going to look at the number at the bottom, the 1716. And the way that we got that in Pascal's triangle, if we're going back to the original way it was made, was by adding the two numbers above it, which would be this one plus the 792. Well, the 792 is not in the stick, but the 792 is made up of the 462 plus 330. 330 is not in the stick, but it is made up of 210 plus 110, 120. 120 was made up of 84 plus 36. 36 was made up of 28 plus 8. 8 was made up of 7 plus 1. And 1 was made up of 1 plus nothing. So it actually works out rather nicely that everything in the stick will equal the diagonal stick blade. The flower petal one. Now, before I go into this description, let me actually just highlight one of the flowers here. And I'm going to do the one down in the bottom left here, the 45. Now think of the 45 as being the central part. And I'm going to draw some flower petals around it. I'm going to draw 9, 120, and 55 and highlight them in red. And I'll highlight the others in blue because I think it looks pretty. So there's our flower with the petals around it. Okay, and the first property we're going to look at is not actually a brilliant one to notice. Again, it is just the idea that any number is made up of the two numbers diagonally above it. So in this case, the 45 should equal the 9 plus the 36. But the 45 is also going to equal the 55 minus 10, the two diagonal left bottom ones. And that's just because 10 plus 45 is 55. So rearranging that, you get that. Likewise, 45 is equal to 165 minus 120. Not exciting at all, just another version of the property. What is interesting, though, is if we look at the two alternating colored petals here, and we actually do the product of them. So if I take the red petals, 9 times 120 times 55, I actually have it written down here, so I'll point it out. 9 times 120 times 55 right here. So that's the product of the red petals. It actually works out to be the exact same thing as the product of the blue petals. And I'm not going to prove why that's true here, but it is actually provable if you convert each of these things into a combination. If you think of the 45 or the middle petal as being N choose R, you can rewrite all 6 other petals as a variation of that. So for instance, 9 is going to be one less or one smaller n, so that's going to be n minus 1 choose, in this case, r minus 1, because it's one row diagonally to the left. So you can prove this, I'm just not going to do it. Okay, so those are the flower petal properties. Again, interesting mathematically, I don't know how good that is for problem solving. Squaring by adding. Also not a particularly useful problem solving technique, but an interesting pattern in here. And again, I'm going to just blow it up a little bit. I'll change color just to see how it works. Now, this works if we choose any number in this diagonal row. Technically, we could do this one too, but let's just focus on the diagonal. So the 1, 2, 3, 4, 5. If we choose any number like 3, 3 squared is 9, which I can actually get by doing the sum of those two. 3 squared equals 3 plus 6. 6 squared is 36. Well, that's just 15 plus 21. 9 squared is 81. That's 36 plus 45. So it's kind of neat that the squares of numbers are actually hidden right in Pascal's triangle just by doing a simple addition. Again, I don't know how useful that is for problem solving because I already know how to square a number. It's not that hard. What is interesting is that Pascal's triangle has all these patterns. Okay, so now that we've looked at some interest sake stuff, let's take a look at some actual things that might be useful. So as it turns out, if you add up all of the numbers in a row of Pascal's triangle, something neat happens. Now I'm going to point out that for row numbers, I'm going to start calling them or numbering them at 0 instead of 1. Again, that's because we know that the combination part starts off at 0, choose 0. So I'll do that as 0, 1, 2, 3, 4, 5, 6. And then beside it, I've got all the numbers in that row added together. So the sum of the first row, that's pretty easy to come up with, is 1. Sum of the second row is 1 plus 1 is 2. Next one's 1 plus 2 plus 1, that's 4. 1 plus 3 plus 3 plus 1 is 8. The sum of the next row is 16. The sum of the next row looks like it's 10, 20, 32. And that last row is 64. And my guess is you'll notice a pretty distinct pattern in those. Those are all powers of the number 2. So 2 to the exponent 0 is the sum of the 0th row. 2 to the 1 is the sum of the first row. 2 squared is the sum of the second. And by the way, again, I say first, second, third row, and what I really mean is the 0th row, first row, second row, third row, and so on. Now, if you think about that for just a second, I think you'll figure out why that's true. Since every number is made of the two numbers above it added together, every number in a row is used twice to get the row after it. So in, for instance, the third row, 1 plus 3 plus 3 plus 1, well, this 1 was made up of 1 and 0. The 4 was made up of 1 and 3. The 6 was made up of 3 and 3, and so on. And what it means is that this one got used, or sorry, every number got used twice. The 1 got used for the 1 and the 4. The 3 got used for the 4 and the 6. 4 and the 6. 4 and the 1. So every number getting used twice means the sum of the next row is always going to be double the row above it. Now using that pattern, we could quickly find the sum of the 12th row, and that's just going to be 2 to the 12th, which of course we all know off the top of our heads is 4,096. And if you don't know that off the top of your head, that just means you're a normal human being and you can use your calculator. All right. Again, I wrote this one I wrote this question for Halloween the first time that I actually used it in a lesson. So Halloween examples. Snoopy goes out for Halloween and gets 14 different candies. He sits down and is deciding how many he wants to eat. How many ways can he choose to eat or not eat the candies? Now this question should look very similar from earlier on. This is basically the number of subsets that you can possibly get in a set. So with each of the 14 candies, Snoopy has a choice. He can eat it or not eat it. That gives him 2 options. 2 options for each of the 14 candies should be 2 to the 14 options. And 2 to the 14 is, I don't know, 16,000 something. So that one I actually don't know off the top of my head, despite the fact that it's not that much bigger than the last one. 16,384. All right. The next one we're going to look at is called the additive property. And again, it's really just a way of looking at Pascal's triangle and stating what it is that you did to make it in the first place. So let's start by just describing what it is that we did to make Pascal's triangle. Basically, we made each number by adding the 2 numbers diagonally above it. So each number was made by adding the 2 numbers diagonally above. So that's going to let us actually play a little bit with some of these combinations, remembering that each combination is just a number from Pascal's triangle somewhere. So 4 choose 2 plus 4 choose 3, can I write that as a single combination? And again, I want you to think of it this way. 4 choose 2 is here. 4 choose 3 is the number beside it. If I'm adding them, I'm going to get the number there. Well, that's going to be 1 row down from the one above it. So that's the top number. So our top number here should be 5. We went from 4 to 1 bigger. Our bottom number is in the same diagonal row as the second of the 2 numbers, or the larger of the 2 numbers that we had in our combination. So the bottom number is going to be 3. And if we want to double check that, we can pretty quickly. Let's pick up my calculator and do 5 choose 3 is 10. Well, 4 choose 2 is 6. 4 choose 3 is 4. 6 plus 4 is 10. Yeah, that seems to work. Similar logic for the next one. 7 choose 5 plus 7 choose 6. As long as these have the same top number and the bottom two are consecutive, this will work. So then this becomes 8 choose 6. The top number gets one bigger than the sevens because it's one row down. The 6 is the same as the larger of the two bottom numbers because it's in the same diagonal row. And then the last one could be written as 17 choose 8. Again, does this property come up a lot in problem solving? Questionable, but it's a property we can look at. Now I want to get to some actual kind of cool problem solving. So the nice thing is there's not really an equation here. It's just a way of looking at a problem. So I'm going to start this one by saying, here's a chessboard or a checkerboard, and we want to move this checker from one side of the board to the other. Now, if you've ever played checkers before, checkers only move diagonally, which means they stay on the same color they started on. And we want to move it from the left side to the right side. I'm going to just blow it up a little bit to make it a little bit easier to view. Here's how I want you to think about it. This checker has two options moving forward. It could go up to that spot, or it could go down to that spot. Those are the only two choices it has. So what I'm going to do in each of these boxes is list the number of ways I can get to that box. So there's only one way I can get to that box, and that's going from the checker bottom or to the bottom and left of it. Or I could get to this box in one way, and again, that's the checker going down and to the right. So now each of these spots could go either of the two directions. There's one way to get here, but there's two ways to get there because I could get there from above or below, and obviously to the left. One way to get there. Oh, by the way, there was only one way for our checker to be in its starting spot. Usually we don't bother labeling it, but there was. And now I think if you look at this sideways, you'll see the numbers 1, 1, 1, 1, 2, 1, which looks like Pascal's triangle. Unfortunately, this pattern's not going to stick around forever, but the idea behind it is. So to move into each of these next boxes, we have to just say how many ways can we get there. This one I can only get there one way. This one I can get there three ways because there was one way to get there from the top left and two ways to get there from the bottom left. So I add those two numbers together. Similarly, this one's a 3 and this one's a 1. I did put a line here, but there was 0 ways of getting there, so there's no real point in even including it. So you know what, just for confusion's sake, let's make that go away. And now our next row, or I should say our next column, there's 4 ways to get here, 6 ways, 4 ways, and 1 way. And you'll notice that now I've slightly broken Pascal's triangle because there's no 1 at the top there, because the board basically cut us off. As soon as the board starts to get in the way and cuts us off, it means that we can no longer have exactly Pascal's triangle pattern. Pascal's triangle assumes that we can go on forever in both directions. To get to this box up here, there's only 4 ways to get there. I can get there 4 ways from the bottom left, and I can't get there from the top because that's off the board. I can get here 10 ways, here 10 ways, and here 5 ways. So there, we've lost our symmetry in that row. 5, 10, 10, 4 is no longer symmetric. It's just because we went off the board a little faster at the top than we did at the bottom. For our next column, we get 14, 20, 15, and 5. And for our last column, there's only 14 ways to get up there. There are 34 ways to get there, 35, and 20. And so the total number of ways to get from one side of the board to the other is 14 plus 34 plus 35 plus 20, which is 93, I believe. 60, 70, 80, 93. Yep, I think that's it. So that was a question that if we had approached it in any other way, we tried to just kind of do trial and error and count the number of ways to get from one side to the other, I think we probably would have been off and would have taken us a lot longer. But if we use what is essentially the pattern of Pascal's triangle, even if it's not identical, it is the idea behind how each number is produced. Add the two numbers above, or in this case, the two numbers from the left, if there are two. Um, and it lets us solve a fairly complex problem relatively easily. One more question for the day, and it's similar to this one, but not exactly the same. I like this one because it's semi-real world. So let's pretend that this grid here is a map. And if I found this is actually really cool, the border that I used for this table. If you look carefully, it looks like little roads. There's little 2-lane roads going all over the place. So we're going to pretend that this is a map of some very small city and that we are in the southwest corner. So we're going to start down here. And we want to get our passenger in our cab up to here. And I want to know how many ways I can get from my starting point to my finishing point, how many different paths I could possibly take to get there. Now we are going to put a little bit of a restriction on this. We're not going to go in circles over and over again because then it would be an infinite number of possible ways. I could just get to one block and drive in circles 1,000 times or 1,001 or 22,855. So I'm only going to head east and north to get from my start to my finish point. However, there still looks like there's a lot of ways to do that. Now, something that will make this one a little bit different from our previous checkers example is that here I'm actually looking at corners of squares, not the middles of squares. So my taxi cab can go north at this point, and there's one way to get here, or it could go east, and there's one way to get to that intersection. And from there, we figure out how many ways it can get to each possible intersection. It can keep heading north, and there's only one way to get these, even though I realize it looks like it went 3 blocks because it did, but the only path that gets me 3 blocks north is north, north, north. There's no other way. Whereas this particular intersection right here has two ways of getting to it. I can go north and then east, or I could go east and then north. I'm going to keep going here. If you want to pause it and try this and then come back and check to see if you're okay, go for it. I'm not going to do too much more on the explanations. I'll just kind of verbally say what I'm adding as I'm adding them. Okay, so here we got 2 plus 1 is 3. 1 plus 2 is 3. 1 plus 3 is 4. That's just 4. Here is 3 plus 3 is 6. 4 and 6 is 10. 10 and 4 is 14. Here, just 3. Now, the neat thing is these ones here, by our definition, you cannot get to. Because, well, I guess you could technically get to 1, but then you can't get to the finish from there without breaking the rules. If we go to any of those, it means we have to go back north, or sorry, we have to go we go south, or we have to go back west, and we're not allowed to do either of those things. So here is 3. 6 plus 3 is 9. 9 plus 3 is 12. 10 plus 9 is 19. And what you're going to start seeing is these numbers getting bigger faster. 14 plus 19 is 33. 19 plus 12 is 31. That one's just 12. This one is 31 plus 12 is 43. This one is 33 plus 31 is 64. And then our finish line should be 64 plus 43 is 107. So that means that there are 107 ways of getting from our starting point to our finishing point. And without doing it in an approach similar to this one, I think you'd have a really hard time coming up with this by just trying to look at it case by case. So this becomes a very powerful problem-solving method for what are fairly real-world problems. How many ways can I get from one place to another? That may matter. Okay, I'm going to stop there. You can go try some Pascal's triangle problems, see how that goes, and we'll catch up with you in the next lesson, which happens to be the last lesson of Unit 3. We'll see you next time.